recording. Okay, so last time we implemented an integer built-in into the language, and now I think we want to do operations on it, right? Operations on it.
Yeah, we have the new data type, but you can't really do anything with it yet other than
Okay,
check
so
for
how does that
equality.
look like in Prolog? How do you actually do a sum?
Uh, well, in standard Prolog, you actually have a plus operator, but it behaves kind of like a three-place predicate,
Oh, so you're talking
where
about like plus like this. So like this becomes a built-in.
um, yeah, Prolog actually has addition expressions, right, with an actual infix operator, but logically it would have to be sugar to something like this in terms of actual, in terms of actual semantics, at least.
Wait, so it has sugar for it. How does the sugar look like?
It's literally just plus. You can do normal arithmetic operations in Prolog.
I I don't know if I'm following what you're saying. Maybe it's better for me to search an example. So let me open an example up here. Let me actually find an example. Okay, so Prolog plus operator. Okay, there we go. X is Prolog syntax and semantics. Wait, are you sure that's sugar though? Like, isn't just like this? Hello?
Mm, yeah, it's basically like that, except that's not really how it looks like this actual surface syntax. Um,
Let's talk only about the syntax.
yeah, it's literally just called plus, but you like if you want to use it with the normal um, syntax, right? The normal predicate syntax. You actually have to quote it because otherwise it's going to try to parse it as an expression, right?
You
As
mean
an additional
this?
expression.
And I'm so confused. I don't know if you are confused or I'm confused. Let's start from the beginning. How it looks like syntactically?
You do a variable equals a number plus another number, basically.
Oh, so you're
And
saying this.
yeah, and then dot, and that this sugars to call to a predicate that adds the two numbers and places the z as the output variable, basically.
Ah. Okay, but that sounds like more work though. Because well, of course it's more work. It's syntax sugar. Uh, should we start going with that, or should we try to go with like plus in the beginning and then we try to develop this sugar for it?
I think it's better to go with the plus at the beginning and then go make the sugar later.
Okay. I
Like
have
right
another
now we
question.
don't even like right now we don't even have infix operators, so
Now we're gonna have to change the parser. Yeah. So I have another question. How does Prolog handles overloading?
it
Aside from the
doesn't.
arity, of
As,
course.
as far as I know, it doesn't.
So are we gonna follow that? Like I was kind of thinking like this, or maybe even like this. Because
Mm,
I think it's kind of bad that you can. This name is now forbidden to be used for everyone else.
hmm.
So I was kind of thinking, how can we differentiate that aside from doing type inverse, of course? And I kind of thought, okay, I don't know if this is a thing, but that sounds useful. But let's not think about that right now. Let's just implement plus as a built-in. That sounds fine. So I have actually a question. I actually have a question. Because if you go to machine, I should have OBS open there. Yeah, okay. Yeah, so you have a built-in, right? Are we gonna do more stuff with it? What do I mean by that? Are we gonna go like um because we're gonna have many things in here, right? We're gonna have is integer, plus integer, minus integer, mod integer,
Hmm.
and so on and so forth. Do we want to put like an integer and then do all the operations related to integer in a separate thing and then put that in the built-in, or we are gonna mix everything in the built-in?
Um, I'd rather just put everything in the built-in because
Okay.
otherwise it's another layer of nesting. I'd rather avoid that.
So this requires.
Actually, we don't need to add any arguments to this, and we should probably remove the arguments from the is integer because we're not really using it.
Wait, what? Oh, 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 oh. It's because the. No, wait, I don't follow. What do you mean we don't use it?
I mean, technically we can put an arbitrary register and say, okay, call the predicate, call the is integer built-in on that register, right? On whatever is in that register. We can do that as an optimization because then we don't have to do register shuffling to call the built-ins, right? But we don't really have that yet. We just always use register 0 for is integer. So it's effectively behaving like a normal function call, except it's just a built-in,
Wait, I'm confused. Why are we always
not
using
function
the
call,
register
predicate call.
0? Oops.
Because otherwise that would actually complicate the code generation.
Because otherwise that would rather complicate the code generation. I'm definitely
Well,
not
not,
following
well,
what you're saying, so I'm actually gonna search. Oh, this is the 0.
yeah.
Okay. Um, okay. I guess we can do that. So what we're gonna do? We're gonna do. Wait a moment though. How do we know this is always going to be true?
Because we generate the code.
No, no, no. How do we know that the data will be resting on the on the 0 register temporary?
Because we are generating the code before calling the primitive as if it was a normal predicate call. Which means we set up the arguments before we actually insert this instruction in there.
Set up the arguments.
Hmm.
I'm very confused by that because
Like, before you call a predicate, we have to emit some code to place the arguments in the correct registers, right?
yeah, where are we doing that in here?
In the in the in the part of the code where we emit predicate calls, like
In the part of the code that we emit predicate calls. That's very non-specific. I think we have a lot of code related to many things. Could you be more specific, maybe?
it's inside of I think it's generates body if I'm not mistaken.
Generate body.
No, not generate body.
Maybe
Emit
emit.
body. Yeah, we need to fix the naming
Yeah, there
convention.
we go. Yeah, so we are putting the counter in there, no? Put constant. And then
Put
we
constraint.
we put the counter in there. The counter not is not necessarily 0, right?
It will always be 0 because this is a one-place predicate that we're implementing as an instruction.
Ah, I see what you're saying. Okay, I think I see what you're saying. So we're proposing true, and we don't need this. We don't need the same thing for the plus. That's what you're saying.
We don't because we're going to write in the source code a three-place predicate called plus, right? We're just going to replace the call instruction with the actual primitive instruction, you know?
Okay.
But the argument setup we're already doing because we're just reusing the same function that that generates the code for normal predicate calls.
Okay. Cool. Um, so I removed from both these integer and plus integer. So let's actually replace this with a plus. And this is a 3 argument thing, right? And then we do plus integer in there. That's what we do. And now, the question is, the question is, wait, see what's going on here? We're matching on the integer. We're mathing on the integer because we're matching on the constant, and that is holding up a number. And we were adding an instruction with the number in there. Oh,
Oh,
but
that's
that no
because
no, but that's a
that's
different
that's
thing, right?
that's a different thing, Lemos. This is where
Yeah.
we need to push an integer into some register. Yeah, no, this should stay as it was.
Yeah. So why it's broken? Let's actually try to run it. Maybe it's broken, but it's just misleading. Okay, it's not. Well, this is misleading, but the evaluator is not. So is integer.
Yeah, this doesn't take a register, and it always uses the register 0, basically.
But that's not how that works.
Cell.x0. Cell.x0.
There we go. Uh, okay. And you're gonna do the same thing with the plus, right?
Yes, but plus is going to be a little bit more involved because it needs to check if at least two of the arguments are already bound.
Oh. Oh, but that's not what this is. Right now this is just the deval step. So in here we say plus integer, and then we're gonna add a plus integer in there. And then here we're gonna put the arguments. You said that we can control the arguments in here, right?
Yeah, just do 1 and 2, x1 and x2.
So cell x1, cell x2.
X2.
Okay, and then we can go to is integer, and then we need to do something. And here I think is where we're gonna do what you're talking about. So
Yeah,
plus, and this is a triplet. So let's call this register 1, register 2, and register 3. And the type of that is this, but twice. And okay, that's what we're talking about. We need to check if 2 of these things are integers.
we need to check if two of these things are bound to integers, yeah.
So it isn't just a matter of calling is integer.
No, because we also need,
No.
well, first of all, we have registers. We need to look at cells instead. So we need to grab the contents of the registers from the computer first.
Okay, so you're gonna be doing, oops. Actually, I think I'm gonna rename this. I'm gonna do 0, 1, and 2. What else?
Then, now that we have the cells, we need to check if at least two of them are integers.
What do you mean by at least true? Are we talking about doing other possible combinations in here?
The third one can be a variable instead.
No. But that's not what I asked. What I asked is that you said that we have to have at least two numbers, right? But
Yeah.
this is a logic language, which means that the number could be in the answer.
Yes, we need to check all the possible combinations of cells to see, like, we need at least two of the cells to be bound, and if the three of them are bound, that's fine. We need to check if the addition actually holds.
That sounds like a very bad pattern matching, but let's try something. We have our patterns. So cell 1, cell 2 with. So the first way is if we have three constants, right?
If we have three constants and we need to check if they are all integers and if the first two add up to the third one.
Okay. So we are talking about, I don't know, having an x0 maybe here. And we're gonna do, man, that's gonna look pretty bad, huh? We're gonna do that 3 times, but this is a true, and this is a 1. And if that's the
When
case,
when there's a side condition, when x0 plus x1 equals x2,
then this is
we just return the computer basically.
that is okay. We just return the computer. Let's actually nuke all of this. Okay, now it comes the problem, right?
Right.
Now it comes the fucking problem.
Yeah, there are basically three cases. If either the first argument or the second or the third is a variable and the other two are integers, we have to do some maths, some arithmetic,
No, but
because
you
if
are
we
flattening. The way that you're saying is flattening the cases in there.
yeah, no, those are three separate cases. They actually do different things.
No. I mean, the amount of possibilities. Right now, the main problem that I'm trying to solve in my head is how can we use our patterns to try to not have to write by hand all the possible bullshit many times.
I'm not sure that we can because they have different bodies.
I guess you're right. I guess you are right. Okay. So let's first do the one with the variable, I guess. We have to say that the first two are are numbers, and the third one is not. The third one needs to be, well, what else can it be?
It
It
must
needs
be
to
a
be a
reference.
functor, right? A
No,
reference.
it needs to be a reference, yeah.
Why a reference in this case, though?
Because in that case, we have two numbers that we're trying to add and we want the output, right?
Exactly. But why a reference still? Aí?
Because we just did the deref, which means if we have a reference on the third cell, that means the third cell is actually a free variable. It's unbound.
But this should be an error.
It shouldn't.
Wait. Oh, because maybe in the future someone is gonna bound that.
No, because if we have two numbers and the third argument is a free variable, we need to do the addition binds the free variable to the addition.
Bind the fee variable. You're completely right. We have a bind, right?
We do actually. And we
We
just
have.
recently updated it to handle cells, which is very convenient.
Yeah. So plus. Yeah, but this is way more involved than I thought. Okay, what does this return? This return a new computer. This return a new computer. So what do we want to do? We want to say that computer. Wait, isn't that actually it? Don't we
Yeah, we
just
just
need to? Can we just return that?
Yeah, we just need to bind this variable to the result of the addition.
Um, yeah, but we need to wrap the addition. And we don't need the address because the unwrapping of the address happens inside there. Um, I need to name this as well, by the way. So what are we gonna do? We're gonna say
It
as
do you?
reference.
It already has a name.
Oh, this is cell 3. Cell 2,
This is
sorry.
how to yeah.
Yeah, so we do bind. I don't remember the order. We are binding the first, the second, or the other way around?
Bind is actually commutative.
Okay. So that means that we can just do cell 2, and then we can just rewrap this. But this time around, we're gonna do x0, oops, 0 plus x1,
And then you need to pass the computer as well.
and the computer, of course. Okay. And this is gonna be pretty similar throughout the cases, I imagine.
Yeah, but instead of addition, we have to do subtraction in the other two cases.
That makes total sense. So let's copy that. Man, that's not gonna work. Yeah, that's not gonna work.
I think in this case, actually, we can use an OR pattern because those two cases will be pretty similar.
Oh, they will, actually.
Yeah, both of them will have to subtract the result from one of the arguments, one of the inputs.
Yeah, but let's do the first. So this is not gonna go there. It's just gonna go here. And then there will be another case where this, oops, goes here actually. Um, yeah, we don't need that. And that will be, wait, but this needs to be an OR pattern, so I need to wrap everything in parentheses in here. And that, and this. Is that how you do that? Am
You
I
have two bars. You have two bars, Lemos.
2 bars?
Yeah, at the end of this line and at the beginning of the next one.
Wait, so it was right before. You're saying that it's like this.
Yeah.
Okay. Um, okay, cool. So if we have that, what do we need to do? We need to do the same. Well,
We need to
actually,
do x1 minus x0 and we need to bind
no.
the
But that's
reference.
that difference though, because in the reference here is in cell 1, and in here it's cell 0.
Now we should actually name the references to some other name.
Okay.
And it should be the
So
same in both patterns,
cell,
yeah.
cell. Oops.
That needs to go, yeah, before the comma.
I don't
And
think
we need to bind,
that's. Do I
then
need
we need to bind the
parentheses?
cell. Do we need parentheses?
Yeah, I already have the name in there in the other one. Let me try to add parentheses to this shit. Maybe that's what's not being happy about.
I think you need parentheses around the S pattern, no?
You mean in here? I don't think that's how that works. Let's actually see what the compiler tells us. I think that's going to be productive. What do you tells us? This pattern matches values of type A, B, but a pattern was expected which matches values of type cell.t. What is it talking about? It's saying about tuples of only 2 members there. Tuples of only 2 members. Do you follow what's happening there?
Not really, no.
Well, regardless, what do we need to do? We need to do x1 minus
Minus
x0.
x0.
Yeah, I'm very confident that this is not how you do get value. Oh, we removed it. We were using an OR pattern in here. We aren't anymore. because now we are fancy. We're very, very fancy.
Maybe you need to
Let's search
put
the sentence. Maybe you need to put.
maybe you need to put parentheses around the tuple, but I'm not sure.
I find that very hard to believe. Yeah, it's only one thingy. Yeah, so this should be actually right. I actually have no idea what this is mad about. Variable cell must occur. Yeah, there we go. This pattern, but a pattern was expected to match. Okay, now it's working. I don't know why that was. Okay, so you do need the. I thought you didn't need that every time, but apparently you do. There. Yeah,
I think you have an extra close parenthesis, or no, you don't.
I don't. Looks
Uh,
terrible.
yeah, maybe put parentheses around the alias binding with the the as cell.
Oh, do you mean like this? Oh, that's actually very weird. Do I need the extra parentheses now, though? That's a very good question. No? No. Yes, I do.
That's bizarre.
But it compiles. Evaluator exception file uh 537.
Oh, that's what we're writing right now, actually.
No, that's pattern matching failed. Oh, okay, but anyway. What other cases are we missing in here?
What are the cases that we're missing here?
Oh, we're missing every
If
other pattern match. Like we need a catch-all somewhere.
the catch-all is just fail. Return the computer with fail true.
Okay. So catch-all computer with fail. Oops, fail equals true.
The open curly brace goes before the computer, not before the fail.
Like this.
Which
Segmentation
program are you trying?
fault.
Which program are you trying to run, Lemus?
Plus and yep. I guess that makes sense. I guess actually that makes sense. But wait a moment. This is now wrong, right? We can't just do that.
Yeah, this is now wrong. Just rename plus to add or something.
There.
That'll work. That works. Plus.
Uh, okay. But now that means that we can actually use plus as a built-in, which means that we can go to multiply and change it to use the new plus instead.
Yes, we can.
Well, actually, um, yeah, let's do that. Let's actually do that. So we don't need naturals anymore, right? We can just use int instead.
We can just use int instead.
Okay, just a moment. Okay, there we go. So the
We also
net
don't
can
need
go away.
we also don't need plus because we have the built-in.
We don't need plus. That's nice. And now we can just implement, well, we can just use plus from the built-in, right? But there
Actually,
is a
we need to
problem.
replace. Well, we need to replace the multiply the nils with actual zeros now.
Yeah, there's another problem, which is the successor. How are we gonna do the pattern matching?
The pattern matching. What do you mean?
Yeah, because right now plus was using piano numbers to do the arithmetic. Now plus is using numbers, but we're not gonna send numbers to it.
Well, we actually need to use the new addition to do that.
But we don't have negative numbers though, do we?
Don't we?
I think
We
it's better, maybe. Actually, yeah, that's a good question. How do we do stuff like this?
that's just one.
Oh, You're right.
The successor of 0 is 1 lemos.
No, you're definitely right. So, what? This becomes 1. What was I holding? Nothing. So this is 1. I guess this is going to continue to be that, and this will be whatever, right? So, but we need to do a subtraction with it, right?
Yes.
So we need subtraction. Let's implement subtraction.
No, we can use plus. We have integers.
But are we
The question is,
parsing
can
integers probably? Correctly, sorry.
I'm not I'm not sure. We should be, I think. Let's
So how are we doing
see
digits?
Lexer. Yeah, we do have negative numbers actually
Where are you seeing that?
in the Lexer.
Integer.
The question is
Where is the definition of integer?
int in the Lexer.
Oh, this. Okay, we do have negative. Okay, so let's do that. The question is how do we write that, right? Because
It's, it's just
uh,
minus before the
okay, so plus. I don't
no
even know
no
if
no
this works.
no. You need to pull the plus out of the multiply.
But that's very convenient syntax, right? If I could just put that in here, but I understand. So what do? We
This
do
actually
n
yeah, this actually n one minus and
and then
then
prev,
yeah, like that.
and then prev goes here. This looks nice. This looks nice. And then instead of putting this, we just put 4. And instead of putting this, we just put 3.
And we should get 12, hopefully.
Hopefully. That's a very important thing to say. So let's do it. Why not? So multiply 0. How fun.
How interesting. What are the okay, out. Uh huh.
This must mean that unification is wrong, right?
Multiply
Because the only cases
n
that we
0
have
0 0
zeros
and
are
0.
these cases, right?
Yeah.
So, you know, the
Let's
unification is
see.
wrong. Huh.
If we multiply 1, we just add the accumulator to the
Oh,
y.
by the way, this is wrong. Because this should say int on n. Just for good measure.
Um, Let me do a. If we multiply 1 by a number, we just add it to the accumulator. If we multiply n by a number, we add the number to the accumulator and we subtract 1 from n to get the previous number, and we multiply the previous to the same number and the new accumulator. Yeah. This should. Yeah, that should work. Except, is there any caveats? Mm,
Weird. But I'm not sure if it's weird because the plus is not. Let's see the plus again. So in here we're just saying plus integer. This is not doing anything, right? This is just saying, oh, there's a plus. We don't pass the value of the register in there. And then everything is being done by the accumulator. So let's actually look at the accumulator.
did you change the code generator to emit the plus as well?
Yeah, it's there. See here?
Built-in plus integer. Okay. Okay.
Yeah, but this is the only change in here, by the way. I don't know if you need more changes.
We shouldn't, I don't think.
Yeah, so in here we are basically saying 0, 1, 2.
Which is correct.
And then we go to this guy. This guy does a bunch of deref cells on all the registers that we are sending here. And then we do the math.
And
So
then we
is
do
the
the
math
math.
right? This is the correct equals equals, right?
Equals equals tests for physical equality. It's just equals, actually.
Oh, no.
But that's still wrong.
And if we have 0, these in a reference, then we bind cell 2 to the sum of them, putting the constant back in. And if we have references in the inputs, then we just say x1 minus x0 binding the cell to it as well. Otherwise, we just fail. So I'm actually interested to put a print in here before we go into debug mode.
Okay.
So print end line I was here. Because the use cases of our plus should not print that, right? Yeah, doesn't print that. So this is not the problem. So the problem is somewhere else, and I'm gonna bet money on the unification again. Unification keeps breaking, huh? So where do you want to put breakpoints?
I mean, the only place where we're doing where do we want to put the breakpoints? We can put a breakpoint right at the beginning of the multiply tree.
So here.
Yeah.
Okay. I also think we should put this in here. Just then it fails
Uh,
fast if you try to be uh, if you do it use it wrong. This not gonna recurse and go to the plus, so then you discover a problem. It will blow up in here. And what?
hmm.
We didn't reach that. You know what that means? This is the problem. How?
Huh.
Okay, let's set debug to this one. No? Okay.
You
Okay.
deleted an
It
I, Lemos.
ah, but it worked, you see? Yeah, it's reaching here. What are we doing?
Multiply for 3 out, but it's reaching the multiply 0. Did we hit the breakpoint, right?
Yeah,
Can we print the registers?
just to be sure. Yeah. Help.
X.
Why do we have two
We
threes?
That's a good question. We have a reference.
We have two. Well, we have two registers with references to 1000.
Uh, Go back to the code real quick, to the program. Okay, so we hit the debug. We are at the debug.
Yeah,
We
which
should
means
have
that
a zero.
these matched.
Yeah, we should at this point have a zero, a variable, and another zero, right? Which is clearly not. Can you print the code segment in the debugger, please? Let's look at the query. Let's see what's going on there. Put constant integer 4 on x0, integer 3 on x1, put variable. Then we call multiply and halt. Then we're doing get constants.
Where is this one coming from? I'm very confused right now. Is the -1 here by any chance? Yes, it is. I'm
Oh,
very
I think
confused, brother.
this is actually the multiply 4.
Oh. Oh, okay. So this is the base case of the recursion then.
Yeah, we should look at the multiply 3 though. That's where we're hitting the problem.
No, but that's in execution. We're already executing, and we didn't print the thing. We need to add a print before that is not
No, 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 no,
available
no,
via
no,
debug
no.
mode.
Look at the output. Look at the code generated for multiply 3, please.
Multiply 3.
Yeah, print the functor table. There's a command in the debugger for that.
38.
It
There we go. Try me else
okay.
47, allocate 0, get variable x3, get constant.
X1
Uh,
and X2.
Wait a moment. This is
Maybe there's a
multiply
maybe
3. Oh, this is this one.
yeah, maybe there's a bug in the get constant, maybe.
In the code generation or in the implementation?
In the implementation. The code gen is right.
It just calls this. Okay, let me grab the book. So, so get constant, huh? We grab that version of the code in here. Deallocate, unify, set instruction. Yeah, there we go. Okay, so this is how it looks like. So get constant calls get constant from different cell, which is up here. And what do we do? What do we do? We check the store. Well, the check of the store is being done by the dref cell, right?
Yeah, dref cell is basically the store
These two.
address inside of the yeah.
Yeah. So we check if it's a constant. If it's a constant, they need the fail is equal to if they are different. This is how you do different in OCaml, right?
It is.
Okay.
It actually is.
Okay. Um, then, if it's a reference, we do a put on that address, putting the constant in the store, and then we trail the address, and everything else we just fail. So trail it has also changed from last time, I believe. I'm not sure. Trail is down here as an auxiliary function. Backtrack, deref, bind, trail. Okay, so we grab an address, we check if it's smaller than the HTB register or if the H register is smaller than the A and A is smaller than a B. If that's the case, we bump the TR register and we put A as an address inside the trail using the TR register as the address, as the index. So it seems to be alright. What do you think?
Yeah. Um it does seem to be alright.
But we tested this before. I'm very surprised that this is breaking because we tested a case with unification before.
Hmm.
And before it just worked, but now it doesn't. Yeah, now it doesn't. So let's actually check the retry me else in here. Yeah, retry me else. This is a retry me else on the multiply 3, by the way, because the 38 is the multiply 3, the first case.
Yeah.
Um, then we do the retry me else, and what do? We we have a 0 on the first register, and then we have a reference in the second register, and I think that's what happens actually. Yeah, we have an N here, and then we have another 0 in there, and then we have the debug, which is holding everything together.
Hmm.
So yeah, so what do? What do we do? What do we do?
There's a trick we can do actually to make these things easier.
Go on.
Right now, we're calling multiply directly in the query, right?
Yeah.
We can make a predicate that's like just an entry point. We can call it main or whatever, and put the
Man,
multiply in there.
but
Call main
before
in the query and put a debug before the multiply.
but before doing that, can we just check if the plus works?
Sure.
Because I'm starting to have some suspicion. See?
Okay, there's something wrong with plus then.
But that was fast, right? Like I'm running this program, right? I'm running multiply. Yeah.
Oh, actually plus is Yeah, no, this should work in the query as well.
Well, but there is a trick we can do in here. We can just say plus, and then we say that plus x, y, z is debug with a plus.
That's okay. That's perfectly okay.
There we go. Okay, so it's holding. What do you want to see? Man, we really need to add comments to this thing.
Put constant, and then put variable.
Yeah, this is the answer, right? We are trying to see what's the 4 plus 3.
Then we do the call, and then we halt.
Yeah. Uh, what else do you want to see? X registers, maybe? Why do we have 3 integers in there?
0, 1, 2, 3, 3, 4, 5. Yeah, we should only have 3 registers set up, and we should have. Why do I have a reference on register 0 though? That's wrong.
Yeah, but the code we barely touched the code generation, so I actually don't know what can be wrong in here. Like, is this not supposed to be 3? I think this was supposed to be 3, no?
It is 3, yes.
Like, what is wrong? I just added this line.
Uh, can I look at the diff for a second?
The default for this?
Yeah, that's just that. We didn't change much in the machine or the evaluator, right?
In the machine, we added, right? So now we have
We
plus
added.
integer in there. In the evaluator, we actually implemented it. And I think the problem resides in somewhere in here. Like, we are hard coding the register now.
Which is actually correct. That's fine.
No, it doesn't work. And that's all that we did. Here we change the program, here we change the example, here we change the plus example, and that's it. So there's something
Hmm.
wrong with the code generation, right? That's what you're saying.
There might be something wrong. What are the chances that something's wrong in the evaluator as well? Let me try something over here real quick as well. Let's see. Karuta main.
Okay, this is the code for doing the plus way smaller than before.
Hmm. Okay,
Yeah, but man,
so
man, just a question. When we are doing the code generation, right? You see that we are using x3, x4, x5, like. Oh, these are the variables that we chose, right? x0, 1, and 2.
0, 1, and 2 are the registers actually, and 3, 4, and 5 are the ones we allocated, which is not efficient, but it shouldn't cause problems.
No, 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 but these are the values that we chose, right? In the evaluator, 0, 1, and 2.
Yeah.
Okay. And then we do a bunch of put values, and then we call plus, and then we do that. Are we doing the evaluation wrong? Like, are we stupid?
Wait, wait, wait. We're using put values.
Yes, we're using put values in here.
Oh no, actually that makes sense. That makes total sense.
Is this not correct?
We take the 3 registers, we take the computer, and we return another computer. We deref each register to get cells. Then we look at the cells and we do the math. No, this should be fine.
Are we hitting this case?
Halt.
We are not going here. That's wrong, right? That's totally wrong.
But you hit the debug, which is before the actual primitive, right?
How do I disable the thing? Toggle?
Enter. Enter does a step, or it should at least.
It's not, man. We are not going here.
Wait, wait, wait. Go back for a second. Go back to the. Okay. 3 on 0, 4 on 1, 5 on 2. We call the primitive, but we don't go there. Yeah, there's something.
Yeah,
There's
let's
something
look at show
wonky.
here. Something? Oh, this is not. This is. Okay, that's actually annoying. But okay. Inline. Cell show C1, 2, and 3. And I actually want to remove the debug. Yeah, let's just call plus in here. What? Man, we have 2 references.
Yeah, there's something wrong happening there.
But wait, we should have a case where we can have 2 references, right? We need to deref them.
No, 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 no. We have a case where we have 2 constants. 2 references should fail.
Oh, it's wait. 2 references should fail. 2 references should fail. I don't know if I understand that because what if I'm doing this? This can't be computed, right?
Yeah, we have a 3, But then we would have to generate all possible inputs for the left argument and all possible outputs for the right argument as well, which would be it would be kind of complicated to implement. We can try to do that later. I'm pretty sure normal standard Prolog doesn't actually do that.
No, but that then fine. That doesn't matter. But we discovered a problem, right? This is our triplet, and we have a reference, which by the way is the same reference.
Yeah, that's very wrong.
Same reference. How is that possible? Are you sure we can choose the values of the registers down here? Don't they have something already? How can we know that?
Because we are emitting the code that sets up the registers before the call.
Yeah, but how do we know we're emitting that correctly, How can we know
Hmm.
that? Like let's look at the test program again. Let's look at plus like this again.
If we weren't, at least for the non-constant cases, then the other programs would not have worked, Lemos, and they do.
I don't remember. Is put from left to right or right to left?
Put is from left to right.
Okay, so we're putting this on this register, right?
We're doing put constants, then we're doing get variables, and then we're going put values.
Well, put constants in my mind do the left to right as well. So that we are putting these on this register. Am I wrong?
Yeah, no, that's right. Put constant is from left to right as well.
Put constants. Yeah, definitely. Okay, so then we do a call, and look at what we are doing there. We are get variable is right to left, right?
Yes, it is.
So at this point, 0 should have this integer, right?
Yes, it should.
Okay, so these are all useless, right? They do nothing, essentially. Like you said, it
Yeah.
doesn't do
Can
harm, but it shouldn't be a problem.
hmm.
We're missing the values along the way here, man. Like, the code seems to be right to me.
Can you go back to the plus with the z and the debug, and can we just check the Oh, but the registers were already wrong inside of the debug, right? In the call to debug.
Yeah, and again, this is also wrong. This plus doesn't do what it's supposed to do.
I think there might be a case for get variable that we're not handling correctly for when we have a constant.
Get variable. Get variable. There's only one case.
No, not the code gen, the evaluator actually.
Oh, that's what we do.
Hmm.
That's what we do. Yeah, I'm also starting to realize that maybe some of the functions that we already implemented, they handled constants before. And because we didn't have them, we didn't care. So maybe there is a chance that we are missing a case. I find that pretty hard to believe, but oh. We have unify constant, right? But we're not even calling unify constant. We're just doing a plus.
No, unify constant is it would be used if we had a number inside of a functor, but we don't have that in this example.
That's true. Yeah, man. I don't know what the heck we're smoking here, but plus as it is, like these doesn't work and we don't know why. This should definitely work. Like
Can we check the implementation of put constant for a second?
put constant. Put constant is just a set register.
Takes a constant, takes a register, sets the register reg with the constant c.
And that's definitely
Okay.
what's going on here.
Okay, put constant is fine. That means put constant is fine. Get variable. What about is
Put
it put
value.
value?
Yeah, we're using put values in there. Put value. Oops. There.
Wait a
Well, in the
second.
book it doesn't do shit, right? Because they just say, okay, put this in a register. We do actually a lot more.
I mean, the book needs to do something similar when we have. Wait, we're
Wait,
not using y. We're not using y registers, are we?
not in this example.
Yeah. So we hit the x case, which is just a set register, and that's exactly what we're doing.
Dere dereferred cell. Yeah, that's correct now.
It should be dereferenced, actually.
The reference like this.
Yeah.
Yeah, so then we just do the set register then. Okay, so let's look at the code again. Do you think the code is correct? This generated code? We need to start somewhere.
Okay, we're putting the constants in the registers. We're putting a new variable in the register. We're calling the predicate. The predicate shuffles the registers a little bit. X0 to X3, X1 to 4, 2 to 5. We call the debug built-in. Then we do the put values, which is just the reverse operation. And then we just call the plus integer and we deallocate and return and proceed actually.
Yeah, so do we want to see the result of this?
Yeah, do
So
an x, x3 to x0.
how do you already have all this crap?
But that's the fact that we have those references there implies that we somehow put a reference in a register somewhere when we were setting up the arguments for the query.
Yeah, this is not enough, man. This debug mode is not enough because we can't we are not looking at what is going on over here.
Can we change the initial state of the computer to start in debug mode?
We can. We can. Just swap this to true. But if you're gonna do that, we well, this actually already is doing what the heck we're going to do. Okay.
Okay, x, do an x, first of all. We have nothing, great, that's exactly what we expected. So if you step and do an x now,
We have
okay,
there.
it's there, okay, step,
Who is talking?
it's not done.
What's a bat map? It's a batteries map.
Yeah, it's a map from the batteries library.
Which is fucked, by the way. Is that fucked or is the other one fucked, Marinho? I don't remember. We encountered a bug, right? About equality on maps. Remember
Maybe.
that?
I don't remember. I don't remember. I
You
remember.
don't remember?
I remember. No, I
Man,
remember we found a bug, but I don't remember the details.
now the details was we were using bat map and we had to replace it with an int map or whatever, or the other way around. I actually don't remember, but we had a problem with maps. I completely remember this. And I even said maybe we should report that. Maybe I said that. But anyway, so now we are doing another one. So put constant. So if I do an
Do an,
x,
do, yeah, yeah. That's the
no, no,
four and the
no.
three.
That's not what, Nathan. You are not believing me. We added prints, printing the maps, and then we stepped upon something that we should be doing a particular behavior and it didn't. You were not here. My English just not remembering. X. It got fucked. Look.
Wait a second. We're doing a put variable from x0 to x2.
That doesn't make sense, does it?
It really doesn't.
So this is a problem with the code generation.
No, this is actually a problem with the register allocation, Lemos.
Register allocation.
Yep.
I'm confused. Why that's
Because
so?
no, because here's the problem. We should never allocate x0 when we're preparing to call a three-place predicate. We should start allocating from x3, not x0. That's the problem.
But I'm confused. Should we do that?
We already have a way to set the offset for which register we're going to start allocating on. We're just not doing it correctly, I guess, for the query.
For the query, you say?
For the query, yes.
I don't think we do. The init allocator doesn't receive any arguments. I think you're confusing with either the code
No, no,
generation or the
no, no,
compiler.
no, no, no. It's the register allocator, Lemos. That's the problem. We
No,
should
no, no.
never
I'm
allocate.
not saying the problem is not in the register allocator. I'm saying that you said we already have a mechanism to set the offset in which you should start allocating. And I
Yeah,
remember that offset being an argument to the function that does the initial.
that's not a function though. That's just a constant. We should
Yeah,
look for the places that use the initial allocator.
there are not many. I think there's only one actually. I don't. I'm gonna grab it in here. Initial allocator. 134 and 141 in here. So here. Oh, look at this. So this is where we're doing it. We're not passing as an argument in here like we do in other places of the compiler. We actually are doing it in
Because
here.
because that's not actually a function. Yes, that's
And we
not
also
actually a
have in
function.
141, which is this.
But that's fine. Allocate query elements. Yeah, that's the problem. We need to change
X register count.
the X registers count in the query allocation. Yes.
What should be the initial value? The length of this?
It should be the length of the element. Same thing as the allocate loop up there, you know? It's just because otherwise we run the risk of doing what we're doing, which is we're allocating a register that should be reserved for an argument to something else. That's wrong.
Why didn't we catch this before?
Because before everything that we had, both terms, both functors and variables, they would be allocated, right, to some register.
Yeah.
And because we do the allocation in the same order as the values appear in the arguments to the predicate, they would always coincidentally be allocated to whatever argument position they belong.
Wait, so you're saying that before when we only had references and functors?
Yeah, because constants don't get register allocated, Lemos. They don't.
Ah, that's why
You
we need
see?
to skip them. because
Yeah.
we don't register allocate them before. So yeah, I see. I was here 7. So let us remove the I was here. I'm gonna keep this for now. And in a multiply, let's actually Control Z the shit out of this. Yeah. Let's keep the test program for now as well, because maybe we're gonna encounter a different bug. 12. God damn it. That was a problem. Uh, we have we have addition.
And multiplication. Well, actually, we don't have multiplication, but we can implement it relatively, well, better than before at least.
Yeah, we have addition. Okay, so but that means that it should be pretty much straightforward to implement minus and multiply.
Yes, it should be.
Let's do
It
that
should,
and then change the
it should,
factorial.
they should be pretty much the same as plus, but with different operators, you know?
Yeah. So boolean
Multiply also needs to check for zeros, right? But other than that, we should be fine.
minus um, multiply. And then we go to the code gen. And that's actually pretty convenient that we only need to change these guys. So minus multiply. So minus multiply. There we go. And then in here, we copy paste. This probably should be an auxiliary function. And that's why I wanted to extract the integer information before, because then we can make an integer a dedicated function. But for now, this is okay. So minus, and then we're gonna have to implement minus, and we also have. Yeah, but we can at least make a built-in function to handle this, even though it's not full integer. Multiply. Okay. So this is gonna be pretty similar to this, right?
Let's do minus first because that's easier. Multiply has a bunch of corner cases surrounding zero that we will have to think about.
Man, I'm starting to think we should have a built-in. What do you think?
Built-in, yeah, we should probably.
And then we can grab all of this shit and toss it in here. The only problem is that this requires the ref cell. Okay, so modules can be mutually recursive? I don't think they can.
I'm pretty sure we tried that before, and the
Didn't work.
conclusion was no, you cannot. It didn't work.
Ah, fuck. Okay, so let's actually not do that right now. Because we need the ref cell. We need to think a little bit more carefully on how we're gonna do that. Okay, so if we have 3 numbers, the first minus the second, they can if they belong to the same module. Yeah, we did that. We did that before. It was painful. I hate it, but Mageta is right. If we have a reference, we need to say that it is equals to this. And if we have the other way around, we probably just need to put a plus in here.
If we have, well, it depends actually. If we have 1 minus 2 is minus 1. If you have minus 1 and 2, then you can just add them together. That is correct. If you have
Oh, if they
1
are
and minus,
negative.
no. It's if you have 1 and minus 1, yeah, if the right argument to minus is missing, the behavior is different. I think we should actually not do minus. We should actually just implement negate because that's easier, and we can derive minus from plus and negate.
Okay, let's do the negate then. But negate takes 3 arguments?
No, it takes 2.
Um, How is that a Prolog thing built in? Can you do that? Like, how does that look like? This?
No, no, no. It's not logical negate. It's integer negation.
Wait, so there is a function, there is a predicate that you do x, y, and
Yeah,
y is a negation of x?
yeah. I'm not sure if this predicate exists, but this feature should be there somewhere because it's literally just well unary minus essentially.
Well, aside from Lisps, I don't know if this is like
What do you mean? You have tilde in OCaml? No?
tilde in OCaml.
Well, not OCaml, ML actually.
Oh wait. Ah, never mind. I don't want to go there right now. Okay, so do you want to implement negation?
Yeah.
Is that gonna be a predicate, a built-in predicate, or are we just gonna implement it to facilitate our lives?
It should. We should probably make it a built-in predicate actually,
Okay.
instead of minus.
Wait, we're not gonna have minus in the language?
If you have plus and negation, you can derive a minus.
No, but I don't want to derive it. I want to be a built-in, so I don't have to derive it. Isn't that the entire point?
You can put it in a standard library lemos as well.
Oh, okay. And negation integer.
Negate integer.
Negate integer. Why is it better to have the negate as a built-in instead of just having minus as a built-in?
Because then, why is it better? Because it's actually just easier because it's there are fewer cases to consider. Like to implement a gate, there are fewer cases to consider than just if you implement minus, because minus is basically a composition of addition and negation.
Wait, your argument is that it's easier to compose minus out of negation and plus, right?
Yes, because you see, the problem is
But someone
minus
needs
is
to
not.
do that. Why is it not better to make that baked in?
I mean, we could. Um, the thing is, that's annoying to implement. That's all. It's a minor annoyance.
Okay, so okay, that's that's lazy, but okay. Uh,
It's a minor
negate.
annoyance because minus is asymmetric. It's basically plus, but you are calling negate on one argument beforehand. Yeah, yeah.
Okay, but negate has two arguments, right?
Well, as a predicate, yes, it has two arguments because one is the negation of the other. At least
Uh,
one of them must. Yeah, this can be implemented with a single war pattern actually. At least one of the arguments must be bound to a constant. Um, if the or if they are both bound, we just check that they are equal. If that they one is yeah, if they're both bound, we need to check if they are one is the negation of the other. If one is bound and the other is unbound, we just negate the bound one and
no, 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 no,
bind.
don't wait. I am not. I'm not following you. Wait a moment. Okay, now you can go. If one of them, if both of them are bound, we need to check if one is a negation of the other, right?
Yeah, when if constant x0 constant integer x1 when
This
x0 equals the negation of x1. And for OCaml specifically, I'm not sure if it's tilde or if it's just minus actually.
seems to be minus. What
Yeah.
else?
Then we do the OR
Reference.
pattern. If one is bound and the other is a reference, and it doesn't matter which order,
Wait a
we take
moment.
the
There, 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 there. Go.
in that case we take the bound integer,
Oh,
we neg
wait a moment. I
we
think I forgot. Yeah, this. Go.
yeah, we take the integer, we negate it using minus, unary minus, and then we bind the variable to the result of that. And we need to wrap it in a cell integer whatever.
So you do minus this. Oops. This. Right?
Um, yeah, and
Something is
otherwise
wrong.
we fail.
Oh, this is wrong. That's it, right?
Yeah, and otherwise we fail. That's negate integer.
Okay. Uh, are we gonna make the minus as a standard library in Karuta, or we do the minus as using plus integer and negate integer in here?
That's a good question. I would be more inclined to. Hmm, that's a good question, actually. I would
Well,
say it
why
would
you think we
probably
should do
be.
the multiply? Go on.
Let's do it in a standard library for now, but
The problem with that is that now we have a need to make some sort of import system or module system.
that is true.
Multiply integer.
Uh, I suppose we can implement it as a primitive as well and use the negation to help us.
Is this close?
Hmm. Let's see, multiply integer, computer. Um, if we have an integer and a reference, we just multiply them together. That's fine. If we have an integer and a reference and another integer, uh, yeah, there's just one problem, Lemos. The x0 there cannot be.
Oh yeah, there is a limitation on. There is a when clause in both of these, right? Oh, actually, you should panic, right? So if x0.
No, we shouldn't. We should fail.
Wait, wait a moment. You're talking about this case, right?
Yeah, if x0 happens to be
But
0,
but if
then
this is 0, the result is just 0, right? Oh, but yeah, the result is just 0.
no, because the
No, we should
problem.
fail. We should fail. You're right.
Oh, I mean, if x1 happens to be 0, then that's actually fine. But if it isn't,
Ah, okay. Actually, that's a good catch. And x1 is not 0. Then we send this back. But shouldn't this just be like a different type of failure? Like, shouldn't this be like a runtime error?
no, it should just be a fail because you're basically saying, okay, I'm checking if this multiplication relation holds. I see that the left, let's use the left parameter being bound as an example just to make it
Mm-hmm,
easier.
mm-hmm, mm-hmm.
We see that we have a 0 on the left, and we have something that's not a 0 on the right. That will never hold no matter what, because anything times 0 should be 0, right? So it should fail.
You're right. You are right. Like this?
Yeah, we fail. Otherwise, we bind the cell, but there's just a small problem here. These are integers, not rationals, which means if the multiplication is not, if the division is inexact, then we should also fail.
Uh, if the division is inexact, it should also fail.
Yeah,
Ah, It's because this is div. Okay, yeah,
This
this
is
is
yeah, this is integer multiplication.
yeah.
So
Do we have div integer div in OCaml? OCaml int div
we have mod as well actually. We should look at
mod.
the mod. If the mod is 0, then it's okay. If it's not 0, we should fail.
Do we have else ifs in OCaml? This also works. Yeah, we do. Okay, so I guess we can say else if. You said mod, right? So I'm guessing that there is a mod. There's no mod. Mod. No mod.
It might be called RAM instead, actually.
RAM. We do. Okay, so if RAM between x1, x0, if this is different than 0,
We
then
should
we
also
also
fail.
fail. Like this.
Yeah.
Okay. Um, I guess that's something. But now let's rename multiply with multiply. Does the example still work? Yes. Let's now change factorial to use all the new tricks.
Okay.
So we don't need this anymore. We don't need this anymore, and we don't need this anymore, right?
We also don't need the other multiply anymore.
We don't need this anymore. Boom. Nice. So int x, and then we try to do the thing. So this is 1.
That's one, yeah.
And then, well,
Factorial of 0 is
1.
no, actually
No,
factorial of
that's.
0 is the out. Well, it's just dot there actually. We need to check if the out is an integer, but
Wait a moment. Oh, this is the base case. I'm stupid.
yeah,
I thought this was some sort of property like we did with the multiply. Then we have something.
1. That's 1. Well, no, actually that's a number.
That's
That's
something.
n.
We're gonna multiply that something, but then we need to do. Well, let's use all the tricks. So we have negation. Let's put. Well, first we need to do a minus, but we don't have a minus, so we need to do what? Man, it's gonna be real cringe. So
We have to do a negation of 1. No, you can just do plus of -1, Lemos.
yeah, but I want to exhaust the instructions. Plus n
Minus.
minus prev, and then we do it like that, and this is 4. Do you see a problem in here?
Negation minus plus minus previous factorial previous. This should work. Actually, one thing we should do after we implement this operation and check that it's okay, we should probably implement the ordering relations on numbers, less than, greater than, all of those things.
No, that's fine, but is this ready to test?
It should be, I think.
Factorial. Damn.
There we go.
Wait, this is now readable, which means that we can put bigger numbers in here. Damn. Cool. Cool. Arithmetic. We have 30 minutes, so let's do what you said. So, which instructions you want?
Less than or equal to.
Why not both?
No. Less than or equal to.
I Oh, less than. Okay, it's one. What you said. Less than or equal. What else?
Yeah. Uh,
What else do you want in integers?
what else do I want in
Do you want
integers?
division in integers?
We should probably implement integer division, yes, and we should implement it properly by making it a four-place predicate.
Oh, so you can have the
The remainder as well, yeah.
yeah. So div integer. Man, uh, the error, we at some point we need to start caring about error messages because how are we going to report that hey our div predicate has four things instead of three things? Uh, we need to start thinking about
Actually,
error messaging. Er,
actually,
er-
let's call it div mod instead, just to indicate that yeah, this is the division with modulo.
but how that's going to look like in the code?
We just call it div mod. Why not?
Div mod like this,
No dash, no dash.
like this.
Yeah,
I hate it. I hate it.
you hate it.
Yeah. You need to give me something in there.
Why? Okay, you can get the hyphen. Why not?
Okay. How is IO in Prolog? Only Marinho and Magetta knows. I don't.
Prolog is impure, so some built-in predicates just perform effects when you call them.
What else? We have two extra here.
I think that should be fine for now. We can implement more later if we need.
Okay. So I'm gonna kill that. You said that div is a 4. Less than or equal to is what?
2.
True. Wait, true?
Yeah,
Less than or equal to?
yeah.
Oh, it's because the predicate holding is the boolean. I see.
Yeah, you don't need to output a boolean. Why would you do that? This is Prolog.
Well, I already told you this before. I'm not well versed. I'm learning as we go here. Div mod integer. So div mod integer actually takes an extra thing. And then we have less than or equal integer. And this takes only two things. And then we do less than or equal.
Man, I would be very sad if the division operation in OCaml is not Euclidean.
I have no idea if it is or not.
It probably isn't. Euclidean division is sadly uncommon among programming languages.
I forgot what are the properties of that one.
Uh, the most important property is that the remainder is always a natural number. It's never negative.
Mm. Mm-hmm. I see. Div mod. So this takes actually a register 3. And then there is an extra thingy in majingi in here. And then we can do 3 in here. So this sounds well, there's a lot of arguments in here. So what should we do? What should we do? Wait a moment. This is a little bit complicated, no?
A little bit, yeah.
Ah, fuck me. Okay, so let's start with the easy one. Everybody's numbers.
Well, in that case, we need to check that the relation actually holds between those four numbers. So we need to check if x1 divided by, or well, x0 divided by x1 must be equals to x2, and x0 remainder x1 to be equal to x3.
Wait, repeat the second condition there.
X1, the remainder of x0 and x1 needs to be equals to x3.
The remainder. So you're saying RAM x0 x1 equals x3. That's a huge ass line. Okay. That's gonna be painful as fuck. Uh, because the
We can do it pairwise. Um, if we know one pair of numbers, we can derive the other.
yeah, but there's a
Like,
lot of pairs in here, man.
no. If we know the pair on the left, we can derive the pair on the right, and vice versa.
Well, that helps, but that's still not exhaustive. So let's do what you said. So if you don't have the pair on the left, which means you're having references on there.
Yeah, if you have references on the left,
So references in like a here, and then so this is gonna be references zero. Well, this is shadowing now. Do we care about cell zero or original cell zero in this case?
um,
Oh, actually we don't care because if we do, we just use cell zero. That's fine. I'm just retarded. And then in here, we do it like this. We remove that. And we probably don't need parentheses in this case.
oh, there's also the case where only one variable is only one argument is
Yeah, man,
unbound.
that's what I'm talking. I don't like this is gonna be pretty boring. But let's just start with pairs. Later we go to the only one ever. We also have the case of three references, I think, right?
Yeah, if we have three references, we actually should fail because we don't have enough information to derive all of them, and this is not a concurrent language.
Okay, less bad. Okay, let's say that you don't have the pair on the left.
Well, if you don't have the pair on the left, you just do. Well, this is actually where knowing whether division is Euclidean in OCaml would help, because if it was, we could just do.
Let's assume that
Um,
it's not.
okay, let's assume that it's not. Well, if it's not, then we need to know which division it is because there are multiple non-Euclidean divisions.
Okay, so which division okay we use? Truncated division according to AI.
Truncated division. That figures. It's very sad, but it figures. Okay. Um.
Well, in this case, we have the man. We actually should give names for these things. I think this is actually pretty bad. But we can change this later. Let's change for the div. So this is the dividend, right? This is the
Yeah, cell one is the
divisor.
divisor. Yeah.
This is the answer, and this is the
No, this is the quotient, and the other is the remainder.
quotient. Remainder is like this. I keep forgetting.
Yeah, it is.
Okay.
It is.
Okay. So dividend, divisor, quotient, remainder. Yeah, we should definitely change the other operations to also have names because that's way easier. Anyway, so it's truncated division. How can we from the quotient and the remainder, how can we derive the other two?
Well, truncated division, that means it rounds toward, or rather,
It eliminates the fractional
yeah,
portion.
it rounds towards zero, basically, right?
Yeah.
That means the remainder can be negative. The remainder can be negative. I just wish it was
It's so
Euclidean
sad,
division.
yeah, because if we could just say, oh, it's the quotient.
Actually, I'm not sure that we can derive the divisor in this case.
Yeah, that sounds hard.
We can't actually.
So this should just fail. This
Yeah, we should not have this case. This should be part of the default.
catch-all.
It should be part of the catch-all. Yeah.
Okay, what if we have? But are there other cases of only having two pieces of information we can derive the other two?
Well, if we have the dividend and divisor, and we have the quotient or the remainder, we can derive the remaining one.
No. But that's not what I asked. I asked if we have only two out of the four. Is there any combination of having only two we can derive the other two?
Well, if you have the dividend and the divisor, you can
You can
derive the
have the
quotient and
quotient and the
remainder.
reminder. Yeah. So let's actually do that. That sounds like what are we doing here? We definitely should have done that first. So here. So what do? We say
Well, the quotient will be dividends divided by the divisor,
bind
remainder.
quotient uh, cell constant cell integer int div x0 x1 computer,
That,
and
and we should.
then we bind with pipe, sorry, we well essentially this thing again, but in here rem. There we go, right?
Yep.
Cool. So what other pair combinations aside of this one? So what if we have we know that we cannot derive the dividend and the divisor only based on the quotient and the remainder, right? That's what you just said before. Like if you only
Uh,
have these two, we cannot derive these two.
if we have, yeah, if we have the divisor and we have,
Quotient.
we don't have enough information in that case.
Are you sure? Because I'm
Yeah,
feeling
because
that this times this should be. Oh, but we need to add this to get to this, and we don't have this.
yeah, and there are many divisions that have the same quotient potentially
Yeah. Okay, what
with
are
the
the
same
combinations?
divisor.
So dividend and quotient.
Yeah, dividend and quotient that doesn't work. Dividend and remainder also doesn't work because we don't know the
Divisor and
magnitude.
remainder.
If we have the divisor and remainder, yeah, that does. If we have,
That's it. We exhausted all the pairs.
yeah, dividend and divisor, that's easy. Dividend and quotient and dividend and remainder, those. Well, if we have dividend and quotient, yeah, we can figure out the divisor from that actually.
Yeah. So I think that's it. We only have one case of pair, which is the obvious one. So now let's do the other, the one that we only have one reference. Let's actually not do that. Let's add first to the one that we have three references. So if we have three references,
We should fail immediately.
okay, so that's catch-all. Then we need to go to the case where we only have one reference. So let's actually do that. Only one
Um,
reference.
act- Actually, if we have the dividend and divisor, That should always work. So if we have one reference, we should do the computation and check if the value that we got actually matches the result.
No, yeah, but that's what we're about to do, right? Having three numbers.
Yeah. If we have the divisor and the quotient and remainder, we can derive the dividend. If we have the dividend and the quotient and remainder, can we derive the
Yeah, probably
divisor?
most of them you can. Like probably most of the three of the triplets being known, you can derive the fourth. I haven't done all the cases in my head, but probably most of them. So let's just start with having the dividend, the divisor, and the quotient.
We just do
We
the
need to,
division normally and check if the quotient matches,
yeah, so we
basically.
do int div x0, x1, that needs to be equal to x2. If that's the case, then we need to bind the remainder, right?
Yeah.
And uh, that's it.
I-
X2 actually here.
yeah.
Oh, actually, can't we just say quotient? No, 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 not quotient. Yeah, that's it. This is it, actually. Believe it or not. And then else, oh, computer, that's what you wrote. Else we fail.
We can just put the if in the pattern match, no, with as a guard.
Oh, you're right. We can just say when, then we bind. Good catch, Marinho. There we go. Okay, what else? So let's imagine that you have the dividend, the divisor, and the remainder now.
Same thing, we just swap well, the guard with the binding, basically.
Wait, swap the bind with the guard.
Yeah, instead of doing the division in the guard
Oh,
and
we
the
do the
remainder
rem
in
in
the
here,
binding, yeah, you just flip them.
and then in here do the div. Oops. Man, I really don't like this shit. Oh, look at all this boilerplate in here. We should have an auxiliary function. Um, cool. Uh, okay, so now let's say that you have the quotient, the remainder, but you don't have the divisor.
If you don't have the divisor, then
Here we need to do some math, I think.
here we need to do some math. If you don't have the divisor, can you figure it out? Can you figure it out? Hmm. Hmm.
Doesn't seem obvious to me at all. Uh, no, but man, isn't this just like a third grade formula or whatever? Like dividends equals
No, no, no.
quotient times divisor plus remainder.
No, 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 no. If you have, um, yeah, if you have the divisor, you can do that, but not if you have the dividend and you're trying to figure out the divisor.
No, yeah, but we have all the other three here. Like, am I insane? Isn't like divisor, dividend, quotient minus. Like, am I crazy?
Uh, no, it would be dividend minus remainder, all divided by the quotient. Actually, the parenthesis is wrong.
Oh, you're wrong. You're right. Actually, right on that. So it's this, right?
Yeah, the parenthesis goes before the close parenthesis goes before the division.
Yeah, just this, no?
Yeah, that should work actually.
Like, the funny thing is that people ask me, "What did you do?" Well, I just did engineering, and now we're discussing third grade formulas in here. And okay, so this is this is
By the way, this doesn't quite work because you're actually implicitly assuming Euclidean division in that line 571.
But we are only using integer division in here. We're not using the truncated one.
No,
Does
no,
that
no,
make a
but we
difference?
are. We are because the default division in Camel is not the Euclidean. Actually, is that actually true though? Let me see. Man, it's been so long that I got used to Euclidean that I can't do truncated division in my head anymore.
Well, let's do three divided by two. Okay, so the three is dividend.
That doesn't work, Lemus, because when both the quotient and the dividend and divisor are positive, um, all forms of non-Euclidean division. Actually, I agree with Euclidean division. We should do division with negative numbers in the dividend and divisor to figure that out.
What? I'm so confused.
Okay, let me dig up a paper here because I'm pretty sure I this. I'm not sure if I posted it on
No,
the
no, no.
server before.
Let's not do that. Well, maybe we
It's
should
a
do
short
that.
paper. It's a short paper, Lemos. Let me just see if I can find it.
2 = 3 minus
Here.
1 divided by 1. Yeah, man. I don't see the problem. I'm still trying to figure out what's the problem. With fractions also work. The truncation doesn't make a dent in this thing.
Here. This is the paper.
Okay. Yeah, no, that's fine. But uh, man, we're not gonna read the paper 7 minutes to finish.
It's a short paper. It's just 7 pages, Lemos.
No, I'm not gonna read it in 7 minutes to finish the thing.
Well,
Uh,
okay.
is it like, can you try to? I will read it, okay? I will read it, but not now. Can you try to help me
Okay.
understand what's the freaking problem in here?
Okay, there's a helpful table on section 1.3. Look at that, and it should give you an idea of what I mean.
1.3. Well, you should be able to tell me. I don't. That's why I don't like. Okay, so the capital D is probably the dividend, and the non-capital D is probably the divisor, right?
It's the divisor, yeah. And then we have the three algorithms. T for the truncating division, which is what C uses. F is for floor division, which a bunch of languages actually use, and it's kind of neat. And E is the Euclidean division.
Okay.
Magetta is asking if you are illiterate, Lemos.
No, it's just a matter of, well, it's a matter of Marinho explaining to me because he read it, and when you read, you should be able to explain it. And it's a matter of time because we still have to finish the other function, the less than. Um,
Yeah, the division rule is actually the same for all of them. It's just the whether the remainder can be negative or not, I guess, is the main property that differs.
Wait,
Yeah,
the
actually,
T, the F is for floor, the E is for Euclidean, and the T is for what?
truncating.
Oh, it's for truncating. Mm. Okay,
Yeah, see,
so
the differences only appear when one of the either the divisor or dividend is negative.
negative. Yeah. dividend and divisor. Oh, okay, that's why this formula doesn't work. It's because of the negative shit. It's not because of the fractions. Okay.
Uh, Quotient times, well, dividend minus the remainder. Yeah, no, dividend equals quotient times divisor plus remainder. That should hold for all cases. It's just, well, yeah, no, that is, yeah, I was actually wrong. I was misremembering. Yeah, this algebra that you did should work. We can just
Third
use it,
grade
I guess.
algebra, folks. Solid as hell.
Yeah, it's been a while since I last thought about division.
uh, excuses that someone literally would give. Well, whatever. I want to finish my thing. Finish my code. I can read the paper later. Uh, okay, so that means that we can do this. Is that what you're saying?
Yeah, we should be able to do it. Yes.
Okay.
The problem is that we have a division in there, and now it matters whether the whether the OCaml division is Euclidean or not.
Whether the no, but I'm not gonna use OCaml division. This is just none of this is valid OCaml. Okay, I just wrote it because I needed a scratch board. We're gonna use int div.
Which is OCaml's division, yes.
Wait, is that not a, like how can I say? Just a way to say it? This is actually real?
Yeah,
It's the same shit.
it's literally the same. And it's truncating.
Ah, fuck me. Okay, then that's a problem. We need to know which division this is. Well, aside from it's true. Well,
We know which division it is, it's truncating.
no, yeah, but does that messes up this?
Well, what if dividend minus remainder is negative?
So,
Or what if the quotient is negative?
so do they don't implement division correctly? Is that what you're saying? Is less than equal to the quotient? It doesn't say here. We need a REPL. Need a REPL. Uh, Wait a moment. Integer remainder. If a y is not zero, the result satisfies the properties. Oh, it is guaranteeing some properties though. Manin, this should be
Hmm.
enough for us to identify if we can trust the division in here. So it's saying that x divided by y times y plus x mod y is equal to x. So let me think. So this is the quotient. We're multiplying that by the divisor and summing the remainder. Yeah, this is literally kind of what I wrote in here, no? In a way.
Yeah, we can actually use that to derive the correct operations.
Okay, so we can just implement this in the guard and be happy about it. Cool. Where was I? Here.
Yeah, OCaml doesn't do Euclidean division. It's definitely not based.
X1. Let's actually do the operation on the left. So what we're gonna do? Uh, we're gonna do a division at some point with x1, which means that this is actually x2, and we're gonna do
Yes,
int
yes, Nathan. x86 does
div
truncating too. That's why it's the most common one.
x
I don't know about other architectures.
divisor. Oh, wait a moment. This doesn't have a guard. This is just a bind. So yeah, I'm gonna put the result of this thing in here. So we are dividing by the quotient, which means x1, and in here I'm doing a minus with x2. This is it, right, Marinho?
Should be, yeah.
Okay. Next, so next is wait a moment, I got lost. Oh, it's the reference on the dividend. That's what we need to do now. So assuming
Oh, that's easy.
assuming the dividend is the guy missing now, we have, well, it's this, right? Just this thing
Yeah, it's the first formula, yes.
there, and then we do no divisions, so get away. And then what we're gonna do? We're gonna do quotient, which is
Times
x1,
divisor plus remainder.
times divisor, which is x0. So we can actually, oops, x1, and then we can do a plus on x2. Okay. So let's see if we're covering all the cases. So this is missing only the remainder. This is missing the divisor. This is missing, no, sorry, this is missing the quotient. This is missing the divisor, and this is missing the dividend. We have all the three cases of
Oh,
missing
four.
four cases of with one reference. We have one case of having true references. We have one case of everybody are numbers. Everything else should go to the catch-all. Is that it?
Uh, yes, I think so.
Okay, that took a lot of brain effort. But okay, let's now implement the less than to finish today.
Well, that's easy. Both values must be bound. They must both be integers, and they must satisfy less than or equal to, basically.
And we receive only two things. So, if both of them are numbers, we need to check this, actually this. Uh,
Otherwise, we just fail. That's it.
do we compile? Yeah, we do. We do compile. Okay, so we have a lot of operations in here. Oh, we actually have minus the minus program, Marinho. Can we derive minus? Let's derive minus. Why not? We should be able to derive minus. Um, and we also have negative numbers, by the way. So we should be able to do everything. Mu 0. So
Minus
this is
ABC.
just neg.
No, we don't need to do a base case. We can do minus ABC equals, or rather, is proved when.
Minus a b. Actually, these are terrible names. In, out. Well, actually,
No.
this is out, and this is in one and in two.
We need to do the negation of in2. And then
Right.
we just add minus in2 to in1. Plus in1, minus in2 out, basically. And that's in1 actually on the plus instead of.
Yeah, I made a mistake in there. So what
And
is
that
this
shouldn't
then?
be int, it should be in actually.
Ah, sorry. This is 4, and this is 2.
And it should have minus 2 in the output. Yeah.
Minus 2.
Well, oh, actually, you should get 2 in the output.
Okay, let's see
Yeah.
what this is. Well, in this case, this is pretty easy, right? Oh, I see what you're doing. The negate is doing the whole asymmetrical portion of the minus. I
Yeah.
see what you're doing. I see. Smart. So minus. What?
We failed to
Mainly
parse.
basics error. Am I blind in here? What are we talking here?
In 1, in 2 out. Neg into minus into. Oh, do we allow numbers in identity lemos?
Numbers in what?
In variable names, actually.
Oh! Oh, okay.
Just do L and R instead of 1 and 2.
Okay. L, R.
There we go.
Poggers, folks.
We
Let
have we have subtraction now.
let's finish let's finish rewriting now triangular numbers. We don't need any of this. Uh, int.
Actually, instead of doing int, we can do that implicitly by saying it needs to be 0 must be less than or equal to n, right?
Ooh, wait. Repeat that?
0 is less than or equal to n. That does the check for the integer as well, and it guarantees we don't get a negative number in the
Ah, I
triangle,
like
right?
that actually. Lac zero.
0 should be on the left.
Yeah, this is man. You there's nothing more you than suggesting to add the freaking less than equals because you hate greater. Like I should have thought of that. I should have thought of that myself. Holy fuck. Uh, fuck readability. We like performance. Um,
Yeah, and then we need to get rid of the remaining unary numbers, right?
yeah, but wait a moment here. So the triangular number in here, this is
Out
just
needs to be an
int,
integer. Yeah.
and then we need to do the same trick that we usually do in here. Which, by the way, reminds me, are we still doing yeah. Um, oh, this is actually, no, let's keep it like this.
You can do.
We
Oh,
can
we
do
don't have
minus,
minus.
but we don't have library system.
Yeah, we don't have a library system. We should fix that at some point.
Okay, so this is gonna be n, and we need to do a -1 in here. So let's actually do something like neg. No,
We
actually I
can
don't like
do
that. Let's just do a direct plus. So we want
n
this, so
minus
minus
one. It's
one
the previous,
prev, and then we do it like that, and then
and
this should be 4.
yeah, and the result should be 10 still.
Um, triangular.
It's just
Yeah,
yeah.
but you see that now it's taking a little while to run. Like this is the first time that I'm a little bit like, okay, this is actually taking a while to compile and do all the stuff. This is the first time that I noticed. And, well, we have a significant amount of code. We can add more stuff now, so let's put 5 in there.
Yeah, triangular numbers, they don't grow nearly as fast as factorial. You can put like
Do we
I don't
have
know,
any sort of puzzle that we can use div mod?
puzzle that we can use div mod. Puzzle.
Yeah, yeah. Well,
Um,
puzzle in quotes. I'm calling triangular numbers and factorial puzzles.
we don't have lists yet, do we?
No.
Uh, we also don't have. Hmm. I suppose we could try to implement We can implement arithmetic modulo 12, I guess. That's clock arithmetic, by the way.
Yeah. We can do hexadecimal conversion.
We can. We can also. We don't have strings though.
So?
um,
Yeah, I think hexadecimal or octal conversion like sounds, which is essentially like the other thing that you said, like mod 12 something. Or
mm,
binary, why not? Convert something to binary. Oh, but that involves having the. Oof. Yeah. Yeah, actually that sucks not having strings.
yeah, strings would be very helpful right now.
Strings would be hella helpful. Let's do an FMT. I actually want to see how the code looks now with that. Yeah, so you broke the tuples. Broke the tuples. Let's actually yeah, let's do that next time. Let's actually just focus on doing this. So this is there is a name for these things, right?
There is, but I always just call them factors, so I don't know how to differentiate the two inputs.
Well, it's gonna be factor one and factor zero and factor one.
Factor L and factor R, why not?
Eh. Are you sure they don't have another name though? Like, I'm
They
pretty confident they have
should,
another name.
they should, but I.
Multiplans?
Oh, it's multiplicand and multiplier, I think.
Multiplicand. Okay, let's actually go with that. Multiplicand. And what is the other one?
Multiplier.
Multiplier. And what is the result of that?
Um,
Product.
the product, yeah, the product.
Third grade stuff, folks. You should remember.
Nomenclature.
Okay. Why are we doing this shit? Oh, because of the OR pattern. That's why. Okay. What about negate? We can call this We can call this factor. Yeah, I think we can call this factor.
It's no, that's not it.
There is a name.
Integer negation. Let's look it up. Uh, Integers, blah blah blah, algebraic properties. Subtraction. Where the heck is? Additive inverse, apparently, is the
Wait.
name of the
The first one.
article. Let's see. Let's see. Opposite number, negative, arithmetic negation, blah blah blah. Where is the name? What's the
I'm
name?
surprised they have a name.
I mean, doesn't everything have a name in mathematics?
Well, yeah, sure, but I'm still surprised. Integer negation operation, maybe.
I guess we can call argument an inverse. Why not?
Okay. Arguments. Am I using? No, I'm not. So inverse. There we go. Okay, for the plus, I think they are called operands, right?
Uh, one is the addend, and the other is
Of course.
I don't know what's the name of the other actually.
Additive?
Actually, I think they are both addends because addition is pretty much always commutative.
Am I using cell 0 any other place? The answer is no. So, what did you say? Addit what?
Addends. Both of
Ad-
them are called addends actually because unlike multiplication, addition is pretty much always commutative.
Addend 1. And what is the result? A sum?
It's the sum, yes.
Sum.
It should be addend with an n. One of them is missing the n.
Okay. Oops. Oops. Int. Okay, so there. Argument and inverse, multiplicand, multiplier, product, then that. What about the less than or equal?
Less than or equal.
I'm almost calling them operands at this point.
Just call them arguments, I guess, or operands, I suppose.
0. Oops. That's not what I wanted to do. Operand 1. You see that it's taking a while now?
Oh, Nathan found a nice a nice thing here that he posted on the chat.
Addition. So there is a term.
Oh, there is an asymmetric terminology for addition actually.
Are you gonna follow the asymmetric to be closer to the multiplication?
No, because multiplication can be non-commutative depending on whether you're using quaternions or arrays,
Yeah,
matrices, I should
matrices.
say.
Yeah. Yeah,
But
okay.
addition is always commutative, so it doesn't make sense to have an asymmetric nomenclature in that case.
Cool. That's cool. Do the FMT. And let's do a commit. Um, yeah, so I think I'm gonna commit all of those. I'm not gonna commit the main there. And then we're gonna do add arithmetic operations on integer literals. Boom, 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 boom.
We have arithmetic, guys. We have arithmetic.
Rework examples. Rework examples to use new integer primitives. And I actually don't care about this change. Okay, I'm gonna finish the recording now.
Bye, future people.